Welcome to the 11th class of this course. In the past few classes, what we did is we took the Legendre differential equation, so which is given by this differential equation, and we found out a power series solution. Okay, this is the power series solution, which consists of two linearly independent solutions, that is this y even and y odd. Okay, and the solution depends on the values of L, and from there, along with the requirement of that the series or the solution should be convergent as at x equals to plus minus 1. So if we put the requirement, then what we basically get is Legendre polynomials, okay, for positive integer values of L along with 0. So this p0x, p1x, p2x, these are all the polynomial solutions of the Legendre differential equations, okay, and these polynomials we are calling Legendre polynomials or Legendre functions of first kind. And then I showed that the same polynomials can also be derived from Rodrigues formula. Okay. So today I will show another method from which we can generate this Legendre polynomials. So the method is called the method of generating function. Okay. So let me define the generating function. So it's kind of a weird function if someone is looking at it for the first time. So phi, let's call it phi a function which is a two variable function. So it has a variable x and h, okay, and it is defined as 1 minus 2xh plus h square whole to the power minus half. So which is nothing but 1 by root under 1 minus 2xh, 1 minus 2xh plus h square. So this function is called the generating function of Legendre polynomial. And how does it generate the Legendre polynomials? Which is in this way. So it can be written as, I'm just stating it, I'm not proving it. So I will prove later. So it can be written as L equals to 0 to infinity plx h to the power L. Okay. So this function, this function, it can be expanded, in a power series of h, and where the coefficients, these will be the plx, these will be the Legendre polynomials. Okay. So this is how it will generate the Legendre polynomials. So if we expand it as a power series of h, then the coefficients of different powers of h, those will give me the different Legendre polynomials. Okay. So which is basically like, so it will give me like p0x plus p1x h plus p2x h square plus dot. Okay, something like that. So this phi is called the generating function. Generating function of Legendre polynomial. So let's check, let's verify that this expansion indeed gives us the Legendre polynomials. So this is not a proof, this is kind of a verification. Okay. After the verification, I will formally prove it. So this is just to show that how you can generate the Legendre polynomials from this generating function. Okay. Right. So phi as a function of x and h, it can be written as 1 minus, let me write in second bracket, so curly bracket, it is 2xh plus, so if I take this minus common, then it will be minus h square to the power minus half. Okay, now we will expand it. So for that, let me first write the binomial expansion formula. So I will use a different color. So let me write the expansion of 1 minus y whole to the power minus n, which is 1 plus ny plus n into n plus 1 divided by 2 factorial times y square plus n into n plus 1 n plus 2 divided by 3 factorial times y cube plus dot dot dot. Okay, higher powers of y. Now here in case of n we have half, right? So let me write it in case of half. So 1 minus y minus half to the power minus half. Okay, minus half equals to 1 plus y by 2 plus, so it is half plus half times half plus 1, that is 3 by 4, right? If I do the multiplication, it will be, so this is 3 by 2 and then half multiplied with it, that is 3 by 4, and there is a 2 factorial in the denominator, so it will be 3 by 8 times y square plus, so it is half times half plus 1 times half plus 2, right? So which is half times 3 by 2 times 5 by 2, so which is 15 divided by 8, right? And there is a 3 factorial here, so it is 48, so 15 by 48 y cube plus dot dot dot. Okay, 15 by 48, I can write it as so basically 15 by 48 I can write it as 5 by 16. Okay, so I will write it as 5 by 16 and higher order terms. Okay, now I will expand this function. Okay, so phi is phi of x comma h is, so here x and h both are variable. Okay, and 1 minus 2xh minus h square whole to the power minus half, and this we can treat as y. Okay, so in that case I can follow this expansion formula and write it as 1 plus half times 2xh minus h square, that is this y. Okay, plus 3 by 8 times 2xh minus h square whole square. Okay, so this term and then this term, which is plus 5 by 16 2xh minus h square whole cube plus all the higher order terms. Okay, So now I will simplify it. So it will be 1 plus, it will be 1 plus xh, right? So it is so 2 cancels, basically there is a half and there is a 2 multiplied with it, and it will be minus minus h square divided by 2 plus 3 by 8. Okay, let me expand it first. So this term I can write as this term, sorry, this term I can write as 4 x square h square. So if I square it, basically if I do the whole square, it will be 4x square h square minus 4x h cube plus h to the power 4. So then it will be basically 3 by 8 times 4x square h square, so which is nothing but 3 by 2 times x square h square, okay, minus 3 by 2 times x h cube, okay, plus 3 by 8 times h to the power 4, right, plus this term, this 5 by 16 times 2xh minus h square whole cube, plus all the other terms, okay. So now what you are expecting, so how we can generate the Legendre polynomials, this is by writing it like this in a power series of h, okay. So this is how we want to write it. So in that case I will first write the constant term, which is 1, then I will write those terms which are linear in h, okay. So where h has a power of 1, that means there is only one such term, okay, that is this one. Now I will write those terms which is quadratic in h, that means where h has a power of 2. So there are 2 such terms, right? So if I write them, then it will be if I take half common, then it will be 3x square minus 1 times h square, okay. And then I can write those terms where h is a power of 3, okay. So cubic, those are which are cubic in h, okay. So those terms will be here. Now I can see one term here from, I mean here I can see already one term, that is so if I take this half outside, then if I take this half outside, then it will be basically minus 3x, right, the contribution from this term. But will there be, I mean, is it the only term? Is it the only term that is cubic in h? And the answer is no. If you look at the next expansion term, you will see there is, so if I do this, if I calculate this, then you can see the first term will be cubic in h, okay. It is 2x h whole cube, right? So in that case, this term will be the first term will be cubic in h, and that term will be 5 by 16 times so 2x h whole cube, that means it is 8, 2 cube is 8, x cube and h cube, and which is nothing but 5 by 2 x cube h cube, okay. So then if I write it, so then it is basically 5, so half I took outside, so it will be 5x cube, okay. And then there will be then you can gather the other terms which are, you know, where h has a power of 4, and then the other terms where h has a power of 5, okay, plus dot all the other terms, right. So the coefficient of h cube, it is coming from this term, okay, it is coming from this term and this term, okay. the coefficient of h square, okay, this one, it is coming from this term as well as this term, okay, and this is the coefficient of h, and this is the coefficient of h to the power 0. This is the constant term. And now if I compare it with this definition, that is, I can claiming that, okay, I can write it as p0x plus p1x h plus p2x h square plus p3x h cube plus dot dot dot, okay. So then our p0x will be 1. Okay. I'm just comparing the coefficient of same powers of h basically. So if I compare the coefficient of h, then it will be p1x equals to x, right? If I compare the power of x square, then it will be p2x equals to, so these terms, this p2x equals to this term, which is half 3x square minus 1, okay. P3x will be half 5x cube minus 3x, and so on, okay. So what I showed is, so it's rather a verification that from this generating function, which is defined in such a way, the Legendre polynomials can be generated, okay, and it can be generated as a coefficient of, as a coefficient in the expansion, in the power series expansion of h, basically in this way. So this is what just now we have verified. So as a homework, you can calculate p4x and p5x and verify with your previous result. Okay, so as a homework, so previous result means I have asked you to calculate this p4x and p5x both from this solving Legendre differential equation and from this Rodrigues formula, okay. So what I am asking now is to verify is to calculate this p4x and p5x from this generating function and verify that, okay, they are same as we already generated, or you already generated, okay. But remember, this is not a proof, this is a verification. So let me now prove that, okay, I can really write this this function as this, okay, as sum over plx h to the power l, okay, and where this plx, these are actually the Legendre polynomials. So the proof, the claim is basically phi of xh equals to 1 minus 2xh plus h square whole to the power minus half equals to sum over plx h to the power l equals to 0 to infinity. Now if I want to prove that, okay, this plx is actually the Legendre polynomials, what I need to prove is, basically I need to show two things. One is plx, these plx's that we can have by expanding this function to these PLXs satisfies the Legendre differential equation. Okay, and that's not the only thing we have to prove. We have to also show that PL1 equals to 1. So it will basically so the first, so if I prove that okay PLX satisfies the Legendre differential equation, so it basically proves that okay whatever you have is the Legendre polynomial subjected to a normalization factor. Okay, so to prove actually that okay this is indeed the Legendre polynomials, we have to also show that okay PL1 is 1. So in that case the proof will be complete. Okay, so these are the two things we need to prove. In case of Rodrigues formula also we prove these two things basically. Okay, so the first proof is the second proof is very simple. So let's say I want to show that PL1 equals to 1. Right? Let's do this proof first. So our generating function is phi xh, I'm writing it again and again, 1 minus 2xh plus h square whole to the power minus half equals to sum over L equals to 0 to infinity PLX h to the power L. Okay, so now 1 minus 2x I can write phi 1h, right? So instead of x I'm writing 1, so in that case it will be 1 minus 2h plus h square whole to the power minus half. Okay, I can write it as 1 by 1 minus 2h plus h square whole to the power half equals to sum over PL1 h to the power L equals to 0 to infinity. Okay, and now let's look at this term. So I can then write it as equals to, so this is nothing but 1 minus h whole square to the power half, right, to the power half, and that is nothing but 1 minus h. So it is basically 1 by 1 minus h. And now if I expand it, if I do the binomial expansion, that is 1 minus h to the power minus 1, then it is 1 plus h square plus h cube plus dot dot dot. Okay, and that is h to the power L equals to 0 to infinity. So if you compare these two expressions, the conclusion is basically PL1 equals to 1, right? So here h has both are equal, and here h has a coefficient of PL1 h to the power L, and here h to the power L has a coefficient of 1, so then PL1 should be 1. Okay, so this proof is very straightforward. Okay, and the other thing that we need to prove is PLX, those whatever are there as a coefficient of h to the power L, those actually satisfies the Legendre differential equation. Okay, so the proof of that PLX satisfies the Legendre differential equation. Okay, so phi as a function of x and h, we have 1 by root under 1 minus 2 xh plus h square, which we can write as, we are claiming that we can write it as plx h to the power l equals to 0 to infinity, right? Now I will give you a few homeworks, that is calculate del phi del x. Okay, so these are homeworks. Calculate del phi del x, and so remember that phi is a function of x and h, and this del phi del x is the partial derivative of phi with respect to x. Okay, so while calculating del phi del x, you need to treat h as a constant. Okay, then calculate del 2 phi del x2, okay, second order partial derivative. Then calculate del 2 del h2 partial derivative with respect to h of h times phi. Okay, so if you calculate those, these are basically 10 plus 2 level partial differentiation. If you calculate, so you should take phi as this, you should take phi as this, and then calculate these expressions, and then if you put them together like this, so like 1 minus x square del 2 phi del x2 minus 2x del phi del x plus h times del 2 phi del h2 of h phi, then you will get 0. Okay, after, I mean, you should put them together and do some simplification, and you will get 0. So prove that, prove it, where you should assume phi as this. Okay, you should take phi as this. So take phi as 1 by root under 1 minus 2xh plus h square and show it. Okay, it's basically a 10 plus 2 level partial differentiation problem. Now once you have showed it, what the steps after that is basically, now instead of phi I will write this expression, and if I write it, so then basically del 2 phi del x2 is nothing but sum over L equals to 0 to infinity p double dash x pl double dash x h to the power L. Okay, so h will not get affected while we are doing the partial derivative with respect to x, right? Similarly, del phi del x, it will be L equals to 0 to infinity pl dash x h to the power L, and del 2 phi del h2, sorry, del 2 del h2 of h phi times h. So throughout these calculations I am assuming phi as this, I am assuming phi as this. Okay, and what you need to, when you will be proving this expression, you need to assume phi as this. So if I calculate it, it will be h times del 2 del h2 of sum over plx h to the power L plus 1. Okay, L equals to 0 to infinity. So now it's a double derivative, so it will be h times del del h. So if I do the double derivative, I can write it directly. So it is L equals to 0 to infinity plx times L plus 1 times L times h to the power L minus 1. Okay, after the double derivative with respect to h. And now if I multiply it with this h, then it will be this h, then it will be it will be sum over L equals to 0 to infinity L into L plus 1 PLX h to the power L. Okay, and now if I put them together, and make so this, and they will follow this expression that I mean, you should prove that okay, they will follow this expression. So if we now put these calculated these expressions in this expression, then what we will get is basically 1 minus x square, okay, and del 2 phi del x2, which is this that is sum over L equals to 0 to infinity p double dash pl double dash x h to the power L minus 2x, this is the 2x, okay, del phi del x is this, so it is sum over L equals to 0 to infinity pl dash x h to the power L, okay, and plus this, so this also we have calculated, which is sum over L equals to 0 to infinity L into L plus 1 PLX h to the power L equals to 0. Okay. So now we will put them together. So it is L equals to 0 to infinity 1 minus x square times p double dash Lx minus 2x pl dash x plus, so I am taking this h to the power L common because it is present in all the terms, so plus L into L plus 1 times PLX, okay, whole multiplied with h to the power L equals to 0. So this is a power series with respect to h, and the right hand side is 0. That means we can say that okay, the coefficients are always 0, okay, all the coefficients are 0. So we will basically put all these terms equals to 0, and if I do that, then if I do it, then it is basically, so what I am doing is basically we have L equals to 0 to infinity alpha L h to the power L equals to 0, here h is a variable and alpha L are the constant coefficients. So in that case I can write all the ALs are 0, that we already showed in the second class or third class, I think. So if I make it 0, then what we are left with is 1 minus x square p double dash Lx minus 2x p dash Lx plus L into L plus 1 PLX equals to 0, and I think you can immediately recognize this expression. Okay, so this is basically the Legendre differential equation, okay, where this y is basically PLX. So what it shows basically that what it proves is PLX satisfies this is the Legendre differential equation. Legendre differential equation, and PLX satisfies the Legendre differential equation. So our proof is now complete. Okay, PLX satisfies the Legendre differential equation and PL1 equals to 1. So what we have showed is basically that okay, this generating function whatever it is generating here, this is indeed the Legendre polynomials that we already got by solving the Legendre differential equation as well as the Rodrigues formula. Okay. One thing I forgot to mention, And the thing is that while defining the generating function, uh, the h has to be, so mod of h has to be less than 1. Okay, otherwise there will be problem in in the convergence basically. So the function will not be analytic anymore. So I will not prove that, but you can check. I mean, for different cases, for example, let's say h equals to 1. Okay, so in that case this phi x will be, this phi x1, it will be like 1 minus 2x plus 1 to the power minus half. Okay, and which is nothing but 2 times 1 minus x whole to the power minus half. Okay, and which is nothing but root under 2 1 minus x. And now you can see that at x equals to 1, the series or this generating function is not analytic, so you cannot define it. It is undefined. It diverges basically. So it cannot generate these Legendre polynomials in that case where this plx, it is well defined at x equals to 1. Okay, so at x equals to 1, if h equals to 1 for example, then at x equals to 1 the generating function itself is diverging. So it cannot you cannot get a well convergent plx from that function basically at x equals to 1. And if h greater than 1, then then I mean, if x in between minus 1 and 1, then also you will see that the series will diverge for some values of x. It will not be analytic. So in that reason, for that reason, this h, while defining the generating function, the mod of h should always be less than 1. Okay, that's how it is defined. So keep that in mind. So that's all for today's class. In the next class, what I will do is I will solve different recurrence relations. Okay, I will prove different recurrence relations, and there I will be using this generating function. Okay? You will see that how easily we can calculate, or you can prove some recurrence relation using this generating function. So that's all for today. Bye.